Right? Hello, everybody. My name is Dr. Ranjit, and as you might know, today we have assembled here for this live session for this particular course on NDT. This live session is something that I have been wanting to do for some time, but now I'm happy that finally it's happening. And it would have been nice if I could see you all like in a classroom. But nevertheless, I'm happy that I could at least talk to you and listen to you and clarify your doubts and questions if you have any. Okay. So I welcome you all for this live session, and let us go ahead with this. And as I said, we can have your doubts and your questions clarified today. So if you have any questions, any doubt on any of the topics that we have for this particular course, you can either ask me. I could possibly hear you. I should be able to hear you. And then you could see on your screen, you would also have a chat window, and I can also see you through that chat window. So if you want, you can also ask your questions through that chat. I will be happy to answer through that chat also. Okay. So let us get started and just come up with your questions. Yeah. Right. Chat. Yeah, so can you guys see me or hear me? Anybody? I'm here to get any question from you so far. Okay. No, this camera. Can I write here? Okay, so we have the first question from Mr. Manoranjan Srinivasan, and he wants to know whether there were any NDT methods or any other techniques before the NDT methods, came into picture, as to how people would have done NDT before these NDT methods actually came into being. If I've got the question correct, I would try and answer that. Okay. I hope you guys are able to listen to me right now. If you remember the first topic that we picked up, it was on dye penetrant testing, right? And we talked about something about that as to how this dye penetrant testing came into being as an NDT method, right? Even before it was recognized as an NDT method, okay? So this technique would have been used or would have been noticed for us by early potters during their pottery, because as you might know, these earthen pots that you have, they have a lot of pores, right? So if you apply on something, any liquid on those kind of surfaces, those kind of porous surfaces, the liquid will seep in or sometimes seep out, right? So when they used to apply some kind of liquid or some kind of colors, they would have seen this liquid, seeping out through those pores, or if there are any cracks on the surface, they would have seen the liquids coming out through those kind of open channels, which could be a pore or could be a crack. Okay, so that could have been the earliest instance of an NDT, if although it was not recognized at that point as an NDT method, but as I said, it could have been one of the earliest detection of how this kind of liquid can be used as a method to identify the presence of defects on a surface, right? Then it would have been later on, it would have been also noticed by the blacksmiths, because what they do, they take something, hammer it, right? They forge a very hard part, right? And then they immediately immerse it into a liquid, right, to quench it. And sometimes what happens, due to this thermal stresses which are generated due to this sudden quenching, cracks develop on the surface, which we call as quench cracks. And they also would have noticed that out of these quench cracks, the liquid in which the part was dropped is seeping out. Okay, so this could have been the other instance in which this dye penetrant test would have been noticed. Okay, and ultimately, as I would have said during the classes, it was noticed and used by the railways, right, to inspect their rails and wheels. So dye penetrant testing perhaps is the first NDT method to be used as a technique to identify defects on the surface. And it was, as an NDT method, it was first time used by the railways, as I said. So what they did, they took their rails and wheels, and then they used to immerse it in a liquid, for example, like in an oil bath. Okay, allow it for some time so that the liquid can be soaked if there are any cracks or any other open channels. And then after that, they'll take it out, and then they'll put some kind of dust over it. So they will spray some dust on the surface, which is nothing but the developer, which will soak the liquid out if there are any cracks on the surface, for example, where the liquid would have gone inside. And once they applied this dry dust on the surface, this dust will suck out the liquid from the cracks and defects and make it visible to them on the rails and wheels. Okay, so these were some early instances of non-destructive testing before any of these methods actually came into being as NDT techniques. Okay, so I hope I have been able to answer your question. So let us go to the next question now, which is coming on the chat screen right now. Yeah, then we have Sai Harish, who wants to know ultrasonic testing in simple words, which should cover the whole week session. See, Harish, it is difficult to cover the entire week, in few minutes, but I'll try and answer your question so that you'd be able to understand, what ultrasonic testing is in few sentences, or maybe in a couple of things that I'm going to tell you right now. Ultrasonic testing, as you would have seen, is based upon reflection of sound waves. Okay, so in this case, we use sound waves which are in the ultrasonic frequency range, right, which is beyond 20 kilohertz. So this is nothing but you are sending ultrasonic waves or sound waves through a part or a sample, and then when it is getting reflected from a particular interface, that reflection, which is known as echo, because as we all know, the reflection of sound wave is known as echoes. So when the echo is coming back, it is being received by the same transducer which sent the ultrasonic waves into the sample or the part. Okay. So what is happening when you are sending these ultrasonic waves through a part, it can go and hit any interface which is in the path of this sound waves, which could be the back wall, for example. That means the other surface of the sample. If you are sending it from the top surface, ultimately it will go and hit the other surface, which we call as the back wall, the back side of the sample, and then it will be reflected from that interface. Okay. So when it comes back to the transducer, it will receive that signal, and the piezoelectric element, the piezoelectric sensor which is there in the transducer, it will convert that sound waves or the mechanical vibrations into an electrical signal, and that signal will be processed and will be displayed in the display screen that you have in the ultrasonic testing system. Okay, so that echo is displayed as a signal that you see, right? So when the back wall signal comes back, you will see the back wall echo on the display in terms of these two axes: the time axis, which is the x-axis, time or depth, and the y-axis, you have the amplitude of the signal. Okay, so you will see the back wall signal if there is nothing in between the top and bottom surface of the part. Okay. Now let's say if there is any defect in between inside the part, right? So then that defect would also act as another interface which can reflect the ultrasonic waves. Okay, so these ultrasonic waves, when they are traveling through this part, they will also be reflected by this defect. Okay, and this defect echo will also come back to the transducer and will be displayed on the display system, like how the echo from the back wall is displayed. Okay, so what you are going to see, if I can write it and show you here on the screen. If you are watching me, I'm going to share a screen right now. and I'm going to show you how this is going to show up in the display. Okay, so what you do, as I said, you have this part, right, and then you keep your transducer on this top surface. Right, so here, as I said, I'm discussing about how ultrasonic testing works. Okay, so this will send the ultrasonic waves into the sample, and this is your back wall. It will be reflected from the back wall and go back to the transducer. And then when you see the display system, in the display you have this time or depth on the x-axis and amplitude of the signal on the y-axis. So first you are going to see this, this initial pulse, and then this back wall signal will come back, this back wall echo. Now, if you have anything in between, any defect or any crack like this, so as I said, this will also reflect the sound waves, the ultrasonic waves, and this echo will also come back. So you are going to see another echo in between the initial pulse and the back wall echo, and this will be the defect echo. Okay. So this is simply based upon the reflection of sound wave from a particular interface, which could be the defect itself. Okay. Yeah, Harish, so I hope I have been able to answer your question. For further details, please go through the other lectures that we have for this course. And while going through those lectures, as and when you have any doubt, any clarifications, you can always get back to us. Using that forum, that Ask a Question forum, you can ask any number of questions, whatever questions you have, you can ask that. And we'll be happy to answer those questions through the forum, okay, that we have in the registered course, which is going on right now. So let us go to the next question, which is by Chaitanya, and he wants to know what is the difference between surface and subsurface, surface, subsurface, and bulk defects. Okay. So surface, it is obvious. These are the defects which are located near the surface. Okay, which is limited to the surface, close to the surface. Then subsurface, you could say that it is just little below the surface, to a little larger depth compared to what you consider as just the surface. So something little below the depth, little below the surface can be considered as a subsurface. And then bulk means which is much below the surface into the thickness of the sample, which is to a particular distance from the surface inside the material. Okay. To give you an example, if you have, for example, the surface cracks, let's say a fatigue crack, for example, is a surface crack. So that will be the crack will be originating on the surface and propagating on the surface. So it will be open to surface. Okay. Although it may not be visible to naked eye, but this is a defect which is open to surface, right? So this can be called as a subsurface defect. Okay. Then there could be defects which are little below the surface, little below the top surface, but still, within a depth which is not very far from the surface, right? So those kind of defects which lie within this kind of depth, they can be categorized as subsurface. And then you have bulk defects or volume defects. For example, let's say you have a casting or a weld. There are casting defects and there are weld defects, which will be inside the part, right? And which may or may not be in the surface. It can be much below the surface. For example, you can have a blowhole in a casting, or you can have an inclusion in a weld, which is well within the weld below the surface at some depth. So these kind of defects can be categorized as bulk defect or volume defects. Okay. Next, let us go to the next question. Yeah, so now we have Kannan. He wants to know something about liquid penetrant testing. And his question is, while over head part crack checking, there is chance of liquid penetrant may fall down due to gravity, whether existing methods is sufficient to detect the cracks or new steps to be followed. Okay. So he wants to know if you have any overhead parts. Okay, so in those kind of instances, in those kind of scenarios where the part is overhead, whether dye penetrant testing can be used. Okay, so to answer your question, Kannan, all I can say is, as long as you can apply the penetrant and make sure that it goes through the open channels or the defects which are present on the part, you can apply it on any kind of surface, including overhead surface. Okay. So what you can do, for an overhead surface, you can take a spray can for the dye, to apply the dye, and you spray it continuously on the overhead part, although it might drip down. But if you continue to apply it through the spray and allow sufficient time for the liquid dye to seep inside the flaws, if there are any, then it should be possible even to inspect those kind of parts by dye penetrant testing. Okay. Because once the dye is applied, rest of the things are quite easy to do, including the application of developer, because the developer, as you might know, is quite volatile if you are using a spray can or a wet suspension. And if you do not really want to use a wet suspension for the developer, you may also use a dry powder and dust it over the surface. So there you will be able to eliminate at least one of the liquid parts that is in the developer. So if you take proper care, and as I said, if you could ensure that the dye stays for some time, and you allow enough time for the dye to go inside the flaws, it should be possible to inspect overhead parts by dye penetrant testing. Okay. And if not, then you should go to other techniques, like for this kind of, particularly this kind of scenario, we have discussed one technique in magnetic particle testing, wherein you can apply the magnetic particle testing through a viscous slurry. So that viscous slurry can be applied on overhead parts. It's not going to fall down because it is viscous, and it will have the magnetic particles in the slurry. So you can apply that slurry having the magnetic particles, and then you can magnetize the part and do the inspection, right? So if you cannot apply dye penetrant testing in the overhead part, the next best possible option could be magnetic particle testing using this magnetic slurry, which can be applied on the overhead parts. Okay. Delay, right? Yeah, Chetan Kapoor is online and he has a question, but that is not really related to the content of the course as such. But anyway, I will be happy to answer that question. He wants to know, what is the scope of doing level 3 in engineering. Okay. You may know this level 1, level 2, level 3. These are the certification courses which are being offered by a particular body, by a particular organization in India. You might know that, and you can do any of these, either level 1, level 2, level 3, depending on what your experience is and at what level you are as a professional. So depending on that, you can register for any of these certification exams, what they offer time to time, and they also advertise that in their website and also through open media. And once you do, and once you appear for the exam and pass it in any of the levels, let's say level 3, what the question is about, then you will be certified as a level 3 NDT inspectors. Okay, and it can be on any of the techniques. So they sometimes offer it for individual techniques like ultrasonic testing or radiographic testing, or sometimes they also offer on multiple techniques. Okay, so depending on what your requirement is, you can choose any of these certification exams. You can apply for it, pay the exam fees and appear for it, and once you pass it, you will be certified as a level 3 NDT inspector for that particular technique, right? And it might have its own benefits when you actually go and do field work. If you want to be in this field, particularly in the manufacturing area where this is extensively used in quality control and maintenance, then in those kind of areas it would be useful for you as a professional. Okay. Then we have Mayank, and he has a question about ultrasonic testing. And he wants to know why ultrasonic testing is mostly not used in steel pipe testing. Okay. So, ultrasonic testing, as I was discussing in response to one of the questions, it depends on the reflection of sound waves. Okay, and while the sound waves travel through a particular medium, which is actually the part which is being tested in this case, there will be attenuation or absorption. So some sound energy or some energy will be absorbed during this travel path. And remember, it has to go back and forth. Okay, but first you transmit the sound waves and they come back. Okay, so during this flight path, there will be a lot of absorption by the material itself, right? So if you have a material where a lot of absorption happens, a lot of sound wave absorption happens, it might be difficult for you to inspect that kind of part. Okay, and this would depend on what is the internal structure of that material, of that part. Okay, which we call as microstructure. Okay? So in the micro level, what is the structure of the material, that would dictate how much sound wave energy will be absorbed when the sound waves travel through that particular material. Okay, so some of the steels, have certain microstructure, particularly this, for example, stainless steel. 304 kind of stainless steel, they have certain microstructure in which the absorption of sound is very high, right? So if you have that kind of material with that kind of sound absorbing microstructure, it might be difficult for you to do the inspection, because most of the time the signal that comes out from the defects is low in amplitude. And if there are a lot of absorption in the material, then that sound or that echo which is coming out from the defects might be absorbed by the material itself. Okay? So that could be one reason why many of the steel parts are not generally inspected by ultrasonic testing. Okay, so now let us go to the next question, which is by Raghu. And he again has a question about ultrasonic testing. And he wants to know if the front wall itself has a defect, then how to interpret it. Okay. So this will be what is known as a closed surface defect, which is right on the surface. And in order to inspect this kind of defects, you need to ensure that your dead zone of the particular transducer that you have chosen is minimum, right? So if you have known about dead zone, then you know dead zone is a certain depth into the material which cannot be inspected. Okay, and some amount of dead zone is always present in a particular transducer, and that depends on the test frequency, right? So if you want to know the indications which are right on the surface, if you want to inspect flaws which are right on the surface, then as I said, you have to first minimize the dead zone, and that can be done by certain ways. And one of the ways is to go for higher frequency, because frequency and dead zone, these two are inversely related to each other. Higher the frequency, lower will be the dead zone. So if you know that you need to do a closed surface analysis, where you expect the defects and flaws to be present right on the surface, you better go for high frequency transducers. Okay, that is one way of doing it. The other way of avoiding the dead zone and do closed surface analysis is by choosing a probe where you have two elements. This kind of probe is known as a dual element probe, wherein there are two elements in the same probe housing. One element will be used to transmit, and the second element will be used to receive, right? So since there is no conflict between transmission and receiving in the dual element probe, you can avoid the dead zone, right? Because the dead zone effect arises because there is a conflict between transmission and receiving, since the same element is used for transmission as well as for receiving the signal back from the sample, right? So if you can separate out the transmission from the receiving, then this dead zone effect can be avoided. And in that case, you should be able to inspect the closed surface defects. Yeah, now there is a question from Sandeep, and he wants to know how can I detect defect in near field. So this is the same answer. The answer to the previous question. This is the same answer to this question as well. If you think that your defects are within the near field, that means if it is a closed surface defect, closed surface analysis, you first go for high frequency probes. You do the ultrasonic testing using a high frequency transducer, or if you have a dual element probe, you can use that as well to avoid the dead zone effect that primarily comes due to the fluctuations in the near field. Okay, so if you want to do inspection within the near field, either go for high frequency or dual element probes. Yeah, so this is again a question from Mr. Keshav, and this question I have already answered. This is about at level 1, level 2, level 3 kind of NDT certification. So if you want to do it, go ahead and do it. ISNT, which stands for Indian Society for Non-Destructive Testing, they do it regularly, so you can register with them, and then you can do any of the levels. And as I said before, that might be helpful for you in your professional career, right? If you want to take up NDT as a career. Yeah, so Chetan, again, Chetan Kapoor wants to know how he can pursue a career in NDT. So first of all, you can get yourself certified or registered as an NDT professional through these professional bodies, like how I said just now. You can register with them, or as I said, you can also take up any of these level 1, level 2, level 3 kind of certification, and then you get yourself certified in any of these levels. So you will be then considered as a level 2 or level 3 kind of inspector. And once you have that certification with you, and you are known as a certified NDT inspector, you can pursue your career as an NDT professional. And there are demands for this kind of professionals, particularly in the manufacturing and in the automotive industries, where they look for engineers or NDT professionals to do quality check, quality assurance, and also for maintenance of parts. Somebody, Mr. Harish Sharma, wants to know NDT surface test for a solid shaft set workpiece. I do not know how big is the sample, Harish, but if you think that you can apply penetrant on the surface, if you're talking about surface defects, we can go ahead and do it at low cost by dye penetrant testing. Otherwise, you can also explore magnetic particle testing if you have the equipment to magnetize the part. Okay, so if it is about inspecting that kind of part for surface defects, you can go for either of these. Then there is Sandeep Khanna again, and he wants to know something about the different indicators that we use in magnetic particle testing. And he wants to know what is the difference between them. So if you have gone through the magnetic particle testing, you have seen we use different kind of indicators to get an idea about the field strength, the magnetic field which is being applied, the magnitude of that, and also sometimes the direction of the field which is being applied, because these are the two parameters that you need to establish before you start the test, right? So there are different kind of indicators like, Kito's ring, pi gauge, and then we have shims. And what kind of indicators you want to use, that would depend on, first of all, your requirement, right? As to what exactly, what kind of a part you have, or what exactly you are looking for, whether you are looking for both the magnitude of the field and also the direction, or it is enough for you to just to know uh, the magnitude itself and direction you do not really want to establish beforehand, right? So in those kind of cases, you can go ahead for Kitto's ring, where you can just get some indications about the strength or the magnitude of the magnetic field which is being applied to magnetize the part. On the other hand, if you want to know both the magnitude and the direction of the magnetic field which is being applied, then you can go for a pi gauge, for example, which can also indicate the direction of the field. And at times where you think you may have to do the inspection at multiple directions, in those kind of cases, then we choose sims which might have a particular pattern etched onto it at different directions, right? So you can etch a pattern on a sim which will provide some guideline about the direction of the magnetic field in different orientations, right? So depending on what you want to establish, you might choose one of these indicators. But in every case, the purpose is same. You want to know beforehand what is the magnetic field strength and whether it is good enough to magnetize the part. Okay. Okay, so Manoranjan Srinivasan wants to know, I think he is asking about eddy current testing, because lift-off car is associated with eddy current testing. So he wants to know in eddy current testing, how is the lift-off curve and how is the conductivity curve. Particularly, he wants to know why is the conductivity curve different, why it is convex, and why the lift-off curve is concave, right? So in order to explain this, I want to share this screen with you, and you would also get this when you go through this particular chapter. This is all explained over there. So let me try and explain it over here. So in the lift-off curve, what you basically see, you see the inductance against the resistance. So this is the impedance. I mean, the resistance and the inductance L together forms the total resistance of any conductor. So in this case, the sample itself, or the part to be tested, that itself is the conductor, right? And then you use the eddy current probe, which is basically having a current carrying conductor or a current carrying coil inside it, which will carry the current. Okay, and that current will induce some current on the sample, on the part, on the surface of the part, which are known as eddy currents, right? So when it is away from the sample, so that is a point over here, right? So this point indicates the total impedance of the coil inside the probe, right? Which consists of both the inductive component, which is this one here, and also the resistance, which is here. Okay. So a combination of these two, as you know, is uh, the the total resistance or the impedance of the coil when it is away from the sample. So when it is away away from the sample, it is in the air. So there is no eddy current being induced on the sample surface, right? So that means no energy is being drawn up from the coil as such. Okay, it is just carrying the primary current. Now, as you decrease the distance between this probe coil and the surface, then these eddy currents will start getting induced on the sample surface, right? So that means some amount of current will be drawn to induce this eddy current onto the sample surface. In other words, some amount of energy will be taken up from the primary coil, which is in the probe, to induce these eddy currents, right? So as a result of that, the current or energy in the coil will reduce. So as we know, if you go by the Ohm's law, when the current is reduced, that indicates the resistance is increased, right? So this resistance and the inductance that you see in this impedance plot, this is the resistance and the inductance of the coil, right? Now that you are drawing up some energy from the coil and the current is reduced in the coil, as a result of that, the resistance will increase, right? And that is what you see as you decrease the distance, the resistance increases, and that's why the curve goes like this. Okay, the resistance will decrease and the inductance, the resistance will increase and the inductance will decrease, and that's why it goes like a concave curve. And how much current will be drawn from the coil onto the sample surface, that will depend on the conductivity of the sample, right? So if the conductivity sample is more, that obviously means that more current will be flowing on the surface of the sample, right? So that means it will draw more current from the coil, right? So as a result of that, if you take up all the conductivity data in terms of different materials or different conductivity, as you increase the conductivity, the resistance will decrease more and more, right? So this is in the direction of increasing conductivity, right? And as I said, as you increase the conductivity, more current is drawn from the coil, and as a result of that, the resistance of the coil increases, and that is why you see the conductivity curve is going down like this as you increase the conductivity. Okay? So that's how these two curve, the lift-off curve over here and the conductivity curve over here takes up this kind of shapes. Okay, so I hope I have been able to answer your question. Okay, so it's a question from Sandeep Khanna again, and I'm not sure what he's asking here about lateral resolution. I do not know with regard to what technique you are asking this, Sandeep. If you could be a little more specific to the question, I'll come back to that. So we can go to the other question here, which is from another participant here, and he wants to know the difference between near field and dead zone, right? So he wants to know, near field and dead zone sometime is confusing because both are in the same region, right? So to answer your question, I can say that a dead zone is an effect of near field. Okay. So what happens in near field, as you would have seen in the near field, there is a lot of fluctuations in the intensity of the beam, right? And as you go away to higher distances into the far field, these fluctuations gradually die down, and in the far field, eventually this ultrasonic beam becomes uniform in terms of the intensity. Okay? So because of these fluctuations in the near field, what happens, even after transmitting, the piezoelectric element that you have, which is used to generate these ultrasonic waves and transmit them, this will still vibrate even after transmitting. So even after you stop transmitting, this will continue to vibrate because of the fluctuations in the near field, right? So it will kind of continue to transmit, right? And a transducer cannot receive when it is transmitting, right? So that means if an echo comes back quickly to the transmitter, to the transducer, when it is still vibrating, it won't be able to receive it, right? So what I mean to say, if the echo comes back quickly, that indicates that the echo has come from very close to the surface, right? So if there is any discontinuity or any flaw very close to the surface, it reflects back very quickly. So within that time, when the echo comes back, if the transducer is still vibrating, it won't be able to receive that echo. And as a result of that, you won't be able to inspect that particular defect, which is very close to the transducer, right? So this distance, which cannot be inspected close to the transducer, is known as the dead zone, right? So dead zone is a very small distance which lie within the near field. Okay, so near field is a larger distance compared to the dead zone, right? So that's the difference between near field, right? As I said, the dead zone is the effect of the near field fluctuations. Okay, hi Ravi. You want to ask something? This is your first live lecture on ND. So Ravi Ranjan wants to understand the list of equipment used in ultrasonic testing. Okay. All you need, Ravi, in order to do ultrasonic testing, you need that instrument, in which all the components will be assembled together. Although if you have seen the lectures, when we actually explain it theoretically, we try and break down this component in different parts, for somebody to understand clearly. So for the sake of clarification, we try and break it down. For example, you would have seen in the diagram that I might have used in the lectures, you have a pulse generator, right, which is nothing but the transducer that you have. Then in that pulse generator, when the signal is collected, it has to be amplified. So you have an amplifier, and then it goes to a processing unit where the signal is processed, and then finally there is a display, right? So all these parts have their own functions, like the transducer or the ultrasonic pulse generator will generate the pulse and receive it. The amplifier will amplify, and the display system that you have, it will process the signal and display, right? So all these are actually, if you see in a practical ultrasonic testing, all these components, excluding the transducer, all other components are built into one small box, right? So all the electronic parts to process the signal, to supply the current to the transducer, everything is built into that small box. And the front of that box will be the display, where you can see the display of the signal in terms of these two axes that I described in response to one of the questions, the amplitude versus the time. That kind of display you would have on the front face of this box. And along with that, on the fronts, on the sides, you might have the buttons or switches to control different parameters with regard to the test parameters that you want to use. Okay? So all you have this box, a small box, which we call the ultrasonic equipment, and you have different types of ultrasonic transducers. Okay, so if you want to choose a particular type of transducer, particularly in terms of the frequency, you choose a particular frequency, a transducer with a particular frequency like 1 megahertz, 2 megahertz, whatever it is, and then you connect it to the box, right? So the transducer will have a connector at the top, so you can connect a cable to it, and that the cable goes to that box where you have a connector for the cable to connect. So you connect the cable to the box, it gets connected to the instrument, and the instrument supplies current to this transducer and also collect the echoes and signals which will come back. Okay, so all you need is that box and different types of transducers of different frequencies. And if you want to do angle probe analysis, angle probe testing, so you need probes with different angles and so on, right? So transducer is one part, and that unit, that box, is the other. So these are the two main components that you have in ultrasonic testing. Then there is a question about Kannan again. He wants to know how to detect the subsurface or bulk defect on moving parts. So this may not be as straightforward as it sounds. If it is a moving part, then you might have to improvise the technique depending on the requirement. There may be also a necessity to do automation. For example, when you do automatic ultrasonic testing, there are some other accessories which will come along with the instrument that will ensure that the whole thing is done automatically, right? So similar thing might be necessary if you are talking about inspecting moving parts. So you might have other accessories and attachments to ensure that this moving part is being inspected at the locations of interest. Okay. Then there is a question from Sandeep Khanna, and he wants to know, for big surface cylinder, how much current is required for magnetizing the cylinder, and how many parts should be for measuring whole cylinder. Okay. Uh, you know, uh, Sandeep, It would depend on the magnetizing distance as to how far you want to magnetize, and you would have seen the requirement of current depending on the distance between the electrodes. If you are using two electrodes, for example, you know that magnetizing current would depend first of all on the distance between the electrodes and also the thickness of the part. Okay, so these are the two things that you need to consider to calculate the current. So per centimeter of electrode spacing, there is a particular current requirement. So you should consider that, and that current per centimeter would vary when you vary the thickness. Okay, so these are the two things. So probably you can keep in mind while calculating the current requirement for magnetizing the part. If it is some other parts, or any other method, if you want to use for magnetizing the part, for example, like what you are talking about, if you have a cylindrical part, right? So you might want to use a non-contact method of magnetizing it by using a solenoid. So in that case, your solenoid will encircle the part. So the part will be inserted into the solenoid, the hollow solenoid that you have. And depending on what is the ratio between the diameter of your part and the diameter of the solenoid, or the ratio of the cross sections of these two, there is a particular magnetizing distance. Okay, so there are two aspects to it. If your part is closely fitting into the diameter of the solenoid, we call it high fill, as the name suggests. Your part is closely fitting into the solenoid. On the other hand, if the diameter of the part is much lower compared to the diameter of the solenoid, then we call it as low fill. So in these two cases, the effective magnetizing distance from the center of the coil or from the center of the solenoid is fixed. Okay, if I remember case, it is 22 centimeter from either side of the solenoid from the center, which is in case of high fill. Yeah, it's 22 centimeter from the center of the solenoid for the high fill case. And if it is a low fill case, then it is the effective magnetizing distance from either side from the center of the coil is equal to the radius of the coil. Okay, so it will on what kind of magnetizing method you are using. Yeah, so I hope I have been able to answer the questions that you have today, and I'm happy that I was able to interact with you live today, and it was really a good time for me to interact with all of you live. If you have any other question also in future, feel free to come back to us. It may or may not be live, but we would always be happy to get back to you and answer your questions whenever you have one. So please feel free to ask your questions through the forum that you have in the course portal, which is open right now. And we always check the portal continuously, and we are always happy to answer your questions. Okay, so thank you once again for joining the live session.